Alright everybody, welcome to our 7th video for 20-1. This one's going to be about something we call completing the square. So we talked about a few methods that we could use to solve our quadratic equations. One of them was factoring, right? That's where we started. Graphing is another. Quadratic formula is one that's coming later on in this video series. So completing the square is a helpful one, and it links together the idea of isolation, where we can actually get our x variable by itself. Sometimes it's difficult to do that, especially if something's x squared and you have another term that has an x in there. Well, it makes it harder to do it because the x's are in two places where you can't put them together. Completing the square helps in putting the x's in one place, which makes it a little bit easier to do this. Now, if you think about the equations that you see up in the top there, well, we could use factoring to solve them, and all three of them really could be factored if we knew, all the methods to do that. The first one is relatively straightforward. If I were to remember that I could write it as x squared minus 16 is equal to 0, since it's a difference of squares, I'm going to know that x minus 4 multiplied with x plus 4 is equal to 0. And then I've got my zeros out of that as being 4 and negative 4. So I could solve it pretty easily with factoring, but I didn't need to, because really I could have just square rooted both sides and got positive 4 and negative 4 anyways. So sometimes solving by isolation, if it's possible, makes it a little bit easier, especially if you think about this one. Well, if I just add 8 to both sides, then I know that 2x squared is equal to 24, and when I divide both sides by 2, I'm going to get 12. So if I think about trying to factor this, it might have worked, but I might have gotten to a place where I couldn't factor it, because I know if I square root this, I'm going to get positive or negative square root 12, and using what we talked about in the last video, I can say that 12 is 4 times 3. If I were to square root my number and take it outside as a coefficient, well, I know it's plus or minus 2 root 3. Right, so there are my two solutions. Now I know square root of 3 is not a perfect one, so I would have had a decimal, which probably means factoring would be very difficult to do. And you can think about that for the last one as well. If you square root both sides, you get positive or negative root 5. If you add a 1 to both sides, well, there are your two solutions in exact value format. So sometimes factoring works, sometimes it doesn't. And if it doesn't, well, there's another way that we can deal with some of these things, which is called completing the square, which essentially has us take things from our general form, ax squared plus bx plus c, into our vertex form or standard form, where I can see a little bit more about that equation. So with this first one, we'll just take a couple minutes. We'll isolate these ones as well, just to get some of that practice in there. So we'll add a 1 to both sides. So 2x squared is equal to 6. Well, that means if I divide both sides by 2, x squared is equal to 3. And then if you square root both sides to finish this, you get positive or negative square root 3. So you do get two solutions here. The same thing's probably true with the one beside it. So x minus 4 squared is now going to be equal to positive 12 when you add a 12 to both. Square root both sides, so you get plus or minus the square root of 12. Add your 4 to both sides, so you get 4 plus or minus the square root of 12, which again you can reduce to 2 root 3, just like we did before. So I still am going to have two answers. Isolation helped me figure that out. Again, factoring would have been very difficult, or if not impossible, because I would have to multiply everything out, collect like terms, and then I'm probably not even going to be able to factor it because I have an irrational number as part of the solution. Now, if they're of the form x plus p squared is equal to q, in other words, just our standard form rearranged a little bit, you can use the idea of what's a perfect square trinomial to help. So if you remember this pattern, it's one that we talked about a lot in Math 10 when it came to factoring things. So if you had a polynomial that followed this format, we could factor it pretty easy. That also means I should be able to expand it pretty easily as well. So if I think about doing x plus 3 squared, well, most people try to do x squared plus 9 and say they're done. The problem is you're missing out on one of the middle terms. So if you do this the long way, you get x squared plus 3x plus 3x plus 9. The fact that you have those two identical terms in the middle is what people miss, and I actually get x squared plus 6x plus 9. Now if I think about doing this the shortcut way, which is probably the way I'm going to do from here on out, if it's x plus 3 squared, well, I can take my first term and square it to get x squared. For the middle term, we'll take the two terms that are inside the brackets, multiply them together, and then double it. So 3 times x is 3x, doubled for 6x. And then you square the last term. So I can skip that middle step, basically to expand that set of brackets a little bit faster, because we need a lot of other things that we're going to need to do. So if we can save time somewhere, that's going to be really helpful. Now you can go backwards as well into your factored format, just remembering to do everything in reverse. So take your first term, square root it, which is x. Take your last term, square root it, you get 3. And the sign that you're going to have in between them was the sign in between your squared and your x term. So it's going to be a plus, and you've got 2 of them. So you can go from one to the other very, very quickly, which is what we're going to need to do. Now, if I try to think about this, completing the square, well, I'm really going to need a perfect square trinomial to help. That's the key to this. I have to have a perfect square trinomial. And if I look at the equation that I've got to work with, x squared minus 10x plus 3, well, I've got a problem right now in the sense that it's not a perfect square. Right? Even though x squared is a perfect square, I could square root it to get x, but 3 is not. Right? I won't be able to square root 3. So there's something missing from this in order to make it a perfect square polynomial. Now in math, if you change something, you can always undo that change by just introducing the opposite number. So if I add something, I can also take it away at the same time. So in order to make this a perfect square polynomial, we have to include a new number that isn't here right now. So if I think about rewriting this just slightly, right? So I'm just going to introduce a set of brackets, and well, I'm going to leave this 3 on the outside right now. Well, the variables can go together. They're going to be part of my polynomial. Now, I left a space here intentionally because I'm going to include a new number into this. Now, if I've got 10 x's, and I want to figure out, what a perfect square number to this is going to be, well, there's a shortcut we could use to this where basically you take the middle term, you divide it by 2, and then you square it. So if I take my 10 divided by 2, I get 5. I'm going to add 25 as the constant. But since I added that number, we also have to take it away in order for this to have the same value. So really those 25s will cancel out for 0. And I didn't change anything. But if I go to factor this now, I get x minus 5 squared, following our perfect square pattern. I can collect the constants. It's minus 22 is equal to 0. And I should be able to graph this to check that they really are the same thing. So you can graph it either in Desmos in your graphing calculator. You'll see the same picture. But now I'm actually able to solve this. Right? I can add 22 to both sides. You can square root both sides like we've done in the past, so plus or minus the square root of 22. And then you can add a 5 to both sides, so x is equal to 5 plus or minus the square root of 22. Okay, so I couldn't really factor it before because you can't really find two numbers that multiply to a positive 3 and add to 10. So factoring's out. You could graph it, but if I follow this method and make it a perfect square polynomial, you can use the idea of isolation to solve for this. And this will work every time. You might have fractions. The one that I'm just going to take a second here to talk about is the one underneath. The numbers are a little bit smaller, so think about what we actually have. So I'm going to draw you a picture. You've got an x squared, which is positive. You've got 4 x's. So if I just think about these algebra tiles for a second, right there's my positive 4. and, well, here's 3 negative 1s. Now with the tools that I have right now, I should be able to arrange them in such a way that, you know, I need a square. So maybe this is a little easier if I use, instead of a drawing, let me open up some Algebra Tiles. Okay, so there's some Algebra Tiles here. So the one we're going to think about again, positives are going to be the blue, greens, yellows. Reds will be all the negatives. So here's an x squared. I've got 4 x's again. So 1, 2, 3, and 4. Okay, and I've got minus 3 1s. So 1, 2, and 3. Now the problem is, if I arrange them like I have them, well, it doesn't really look like a square where I try to put things. So the way that I have them, the orientation matters. So I can't really have my x's where I put them, because really that makes a rectangle. So I'm going to delete 2 of these, and I'm going to orient them the other way. Because now I can see the length and width is starting to have the same dimensions. The problem is I can't really fill in this space with the 3 1s that I have. I don't have enough. So let's leave them off to the side for a second. And then there's only one thing that can really go here to solve my problem. Well, if my x's in green are positives, well, that means when I multiply them, the only thing that can go here are 4 positive 1s. So now I really have a square. The dimensions of it are x plus 2 by x plus 2, so there's a literal square we just made. And I still have my 3 1s off on the side, the negatives, but the problem is I changed the value of this. I added in 4 positives that weren't there originally, so I need to take 4 of them away as well. 1, 2, 3, and 4. Okay, so now by putting in those 4 in yellow, I added 4 more in red to account for this. And, well, I have my completed square format, because I have my square off on the left, so really it's x plus 2 squared, and then I've got minus 7 attached to it. So I've got my standard form that I'm supposed to. So let's go put that into, you know, the algebra. So I'm just going to delete this because I've got my picture already thinking, right? I've already got my picture in our mind. So let's do this algebraically. So we put together our x squared and 4x. We left our minus 3 off on the side, right? So it's still equal to 0. The number we added in was the number to complete our square. So we took our x's, we split them into 2 groups. So maybe what we'll do is have that picture side by side here. How do I move this? There we go. We took our green x's, right? We split them into 2 groups. So I had 4 originally. So I took 4 and divided it by 2, and then that number got squared to make my square. So 4 divided by 2 is 2, squared to get us to 4. So I added in a 4 to make my square. I also had to take away 4 to include it with those negatives. So really I've done the same thing, but just in terms of numbers, just algebraically. So if you think about actually completing the square now, my square is complete. So in the factored trinomial format, x plus 2 squared minus 7 is equal to 0. So I've done the same thing, just algebraically. And now I can solve this for the value of an x. X plus 2 squared is equal to 7. X plus 2 is equal to plus or minus the square root of 7 if you square root to get rid of your square. So that means x is equal to negative 2 plus or minus the square root of 7. Oops, there we go. So completing the square works here as well. But then I've got to think about what happens when I've got 3x squared minus 12x minus 9. Really, there's a coefficient here, a greatest common factor, in each of these numbers. Now, if I think back to this in terms of the pictures here, so let's get all these out of here. Well, now I have 3x squareds. I have minus 12x's. Minus 12, and really this is going to be a lot of them. So there's 2, I don't know, okay, so 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There they are. And then we had 9 negative 1s. So 1 here, 2, 3, 4, 5, 6, 7, 8, 9. And the problem is, if I try to arrange them with what I have, I won't be able to make one big square. Right? I can't make one big square. What I can do, however, is make 3 smaller squares with what I have. So let me think about putting, let's get rid of that, and we'll do a horizontal one instead. Get rid of that one, make another horizontal. Okay, so I've got the beginnings of one square, the beginnings of 2 squares, and I've just got enough x's left to put them together with my other square. So there's 2 vertical ones. We'll take out those 2 vertical ones and introduce some horizontals to get our dimensions to match up. Let's move these ones a little bit. And the issue that you can probably see right now, I only have 9 ones. Right? I only have 9 ones, but 3 squares where I'm supposed to put them. And if you look at the bottom, you can tell again that these squares really have the same dimensions as the ones we just talked about. So I'm really going to need 4 positives to finish up each of those squares, just like before. And they're positives because my x's in red are negative, and a negative multiplied with a negative makes a positive. It just happens 4 times to make my square. But it happens 4 times in each of them. Right? So each square that gets created now had 4 ones introduced to it, which really means I didn't just add in 4, I added in 4 3 separate times. So in order to account for this, I can't just add 4 or take 4 away to help us out here, because it's really the opposite. So I'm adding in 4 negatives, but I have to add in 12 negatives. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? Really, I have to take away those 4 positives every single time I added them. So I've got my squares completed. I've got my ones taken care of. I've got everything where it's supposed to be. So I can write the factored form of one of those squares, but just remember I have 3 of them. Right? So it should be 3 multiplied by 1 square, and then all my constants collected. So really, this is like me representing a quadratic equation that has an a value. This has a stretch. Right? There's 3 squares here. Let's go do that algebraically. Okay, so same sort of idea. What we did is we put together the x's, so the squared and the 1. We left out the 9 for now. We just kicked them to the side until we were able to make our squares. And then what we did is we recognized that I couldn't make one big square, so I had to split it into 3 smaller ones. So I took out a common factor of 3 from my first 2 terms only. I didn't deal with the 9, I kind of left it to the side. Now, inside that trinomial, that set of brackets, think about what number we used to make our square. We took our 4 x's, we split them into 2 groups again, and then we squared it. So for each square, we added a 4. The problem is, I didn't take 4 away, I took away 12. And the reason why I took away 12 is because there are 3 times that I added that positive 4. So really, I'm taking away 12 here. Each time I add in a 4, it's like a distributive property. 3 times 4 is 12, but I added 4 to make my square, so I have to take 4 away to counterbalance that. Okay, so same thing represented algebraically. So if you have it factored now, x minus 2 squared minus 21 is equal to 0. Got my factored form, which is identical to this. Right? 3x minus 2 squares, and then there are 21 negatives. So the same thing represented just in terms of an equation. And now I can solve this pretty easily. So 3x minus 2 squared is equal to 21. Divide everything by 3, so that x minus 2 squared is 7. Square root both sides, so x minus 2 is equal to the positive or negative square root of 7, so that x is equal to 2 plus or minus root 7. Okay, so there are your 2 solutions. the picture helps just to visualize it, but it really is only good if they're whole numbers. Fractions cause a little bit of an issue. It's still possible to be done, right? With this tool, I can actually split those x's into pieces. So I can split them up however small I need them to be. So I can do quarters, halves, eighths. I can keep going and making them smaller. But it makes it a little bit cumbersome to do it on here. So we won't do the splitting of them with the fractions. With algebra tiles, we'll stick to the numbers. So we'll do this one as well the exact same way. So the first thing we'll do is we'll split it up, our squares and our x's together. And then what we'll do is factor out a common factor if we can. And if I take that out of 6 there, that's going to be a minus 12x. So remember how to factor out a fraction. So think about distributing at this point, and I should get the same thing. So negative 1/2 x squared, positive 6, that all looks good. Think about the number you have to add to complete your square. Take your 12 x's, cut them in half again, split them into those two groups, and then square it. So 12 over 2 is 6, square 6, and you get plus 36. Now this time, the same rules are true. The number I added in, which is our positive 36, has to get multiplied with our coefficient on the outside, and that'll be the number we put outside the brackets. Right? It's like a distributive property case. So this time, positive 36 multiplies with a half to give us 18, but it's negative 18. Okay, because when I actually multiply this in, that's a negative. So this should work as well. I think. We'll see what happens. I'll graph this after, and we can compare them that way this time. We won't do the algebra tiles. Okay. So that I think looks good. Yes, because I got a neg. Okay. Yeah. All right. Let's go. So negative 1/2. We've got x minus 6 squared minus 19 is equal to 0. So if you're ever unsure that you're ever unsure about your completed square format, what you can do is just graph it. Again, I'm just going to use Desmos because it's easy to plug it in here. So negative 1 over 2 x to the power of 2 plus 6x minus 1. Oh, I put an equal. That's supposed to be a negative. There we go. Okay, so there's the original, negative 1/2 x squared plus 6x minus 1. Here's the one that we think it is, negative 1 over 2 x minus 6 squared minus 19. So I am missing a sign somewhere because, this should actually be a positive, that's why. I really added in a negative, but the fact that there's a minus sign here is what does the opposite thing. So when you distribute this, you get minus 18 in the brackets this time, so I need a positive 18 to cancel it out. There we go. So if I change this now to a positive, what did I still do? Oh, that's not 8. That should be 17. That's why. Because now I changed it. There we go. Collect my numbers the right way. So negative 1 plus 18 is positive 17. So there's my positive. 17 is better. There we go. So even us math teachers forget the signs as well. It happens. So just take your time. Make sure things cancel where they're supposed to. Double check with the graph to make sure you've got the same equation. Okay, there we go. So now it does match perfectly like it's supposed to. Okay, so all looks good. And now we can solve this. So if you think about moving your 17 to the other side, there's my x minus 6 squared is equal to negative 17. And usually we can't square root a negative, but it'll get dealt with when I deal with this fraction because it's a negative as well. The signs will cancel. So multiply everything by negative 2, and you'll find x minus 6 squared is equal to 34. Square root it, and then add 6. So 6 plus or minus the square root of 34 are going to be your two solutions. Okay, so you can still do this with fractions. You can still do it with negatives, provided you just watch the signs, because here I even messed it up. because really what I added in was a negative. It looks like a positive, but multiply it by that coefficient, it's actually a negative, so I have a positive on the other side. Okay, we'll do these last few together as well, because completing the square can be a little challenging, especially with fractions. So nothing's different, right? Really nothing is any different. So I like to split them up first, really show that you're introducing that set of brackets. Factor it out. So there's a half, x squared plus 6x. Think about what you need to complete your square this time. So I'm going to add in 9, because 6 divided by 2 is 3. 3 squared is 9. But the number I'm going to subtract on the other side, or if you like, I'm adding a 9 to the left side of the equal sign. And what you do to one side, you do to the other, the same rule that you've heard since elementary. So I really didn't only add in 9. There's a coefficient there of a half as well. So those are going to combine. And really, it's like me adding 9 over 2 to the other side. Right? Because 9 multiplies with a half to make 9 over 2. So if I add it to the left side of the equal sign, I also add it to the right. If they're on the same side of the equal sign, the signs are backwards, right, to cancel out for 0, which mathematically is the same. So this will be a half x plus 3 squared minus 9 over 2 equals 9 over 2. And if I move my other 9 over 2 to the other side to start solving for this, that ends up being 18 over 2, which works out to just be 9. Multiply by 2 to get rid of your fraction, so that x plus 3 squared is equal to 18. Square root now. Subtract 3, so negative 3 plus or minus the square root of 18. 18 can be written as 9 times 2. Square root the 9 and bring it out front, so you get negative 3 plus or minus 3 square root 2 as your solution. So once you get the hang of the pattern, there really is just one step before you can actually solve for it like we've done before. Okay, we'll do B as well. So I'll change color here so it breaks it up a little bit. Same sort of thing. There's no common factor really between all of them. You could factor a fraction from your constant, but that makes it more challenging. So I usually just don't, and I ignore the constant. So minus 5 x squared, this should be plus 2x. Leave your plus 2 out, so you're only factoring it from the first two terms. Negative 5, negative 10, so that looks good. So take your 2, cut it in half and square it. The number you're adding in is a plus 1 to your brackets, but you do that negative 5 times. So really, you have to remember that this number that I've just added in is a negative. So I'm going to do the opposite to make this work. So I'm going to actually, am I going to add 5? No, I'm going to, yeah, I'm going to add 5. Because I added in a negative. Yeah, so if you distribute, you get a negative 5. See, I always get the signs backwards too. You're going to add in a negative 5, because when you distribute, in order to cancel out that negative 5, you have to add a 5. Again, if you like thinking about it in terms of what I do to one side, I do to the other, really you're subtracting 5 as well on the other side. So you can keep it the same that way too. And we'll graph this one again just to make sure that we've got the signs in the right place. Okay, so there's my number, so there's my minus 5. This ends up being x plus 1 squared plus 2 is equal to minus 5. And if you move your 2 over by subtracting, then negative 5 x plus 1 squared is equal to negative 7. Divide. So you've got x plus 1 squared is equal to 7 over 5, which you can still square root as a fraction. So x plus 1 equals the positive or negative square root of 7 over 5. X is equal to negative 1 plus or minus the square root of 7 over 5. So we'll go check this one in our calculator just to double check and make sure that we've got things where they're supposed to be. So we'll graph this one. I'll graph the original. So negative 5x squared minus 10x plus 2. Here's my two solutions. So let's just double check what. I'll grab my calculator here. Where is it? There it is. So we'll double check that our solutions are those two numbers. Okay, so we'll do -1 plus the square root of 7 divide 5. Okay, I got one of them, 0.183. Check the other one as well, even though I know it's probably going to work. So -1 minus the square root 7 over 5. And there is the other one. Okay, so I have my signs in the right place. I know my solutions are the correct ones because I can see them on my graph. It all looks good. Okay. So we'll do one last one here. It's a little bit more of an application. Projectile problems are pretty common. So you've got a football. It's being kicked vertically, and the approximate height of the football after t seconds is modeled by the formula given to you. So height as a function of time is equal to 1 plus 20t minus 5t squared. When will the football hit the ground is essentially what it's asking. Now if you think about what this situation may look like, you've got a ball being kicked by a person, right? It goes up and then comes down. So there's going to be two spots where, you know, the ground level technically is, right? When I start and after a certain amount of time has happened. Now, only one of these is going to be the right one because I have to kick it first in order for it to hit the ground. So we won't pick the initial point. We're going to pick the one after some time has passed. So we got to figure out when that's going to be. So really, we're looking for our solutions once again. So rearrange this, -5t squared plus 20t plus 1. Solve this by factoring. You can try to do and find two numbers that multiply to 5 and add to 20, but there aren't going to be any. So then you can graph it, but if you have to do it algebraically, graphing's out, I don't know the quadratic formula just quite yet, so my only option is to think about isolation, where I have to complete the square. So take out that -5, you're left with t squared minus 4t. You've got your constant of plus 1 on the end. Think about the number you have to both add and subtract. So I'm going to put in a 2 here. No, I'm going to put in a 4, because 4 divided by 2 is 2, squared is 4. But really what I just did is included 20 negatives, right? If I think about that -5, I included 20 negatives, so I have to include 20 positives, the opposite one, to account for this. Right, so think about doing the opposites if you keep them on the same side. In factored form then, it's -5t minus 2 squared plus 21. Right, there's our function in terms of height. Right, so height in terms of time is this. Well, now I've got to solve this because I'm looking for the zeros, and I'm looking for the zeros in height, so I'm going to make sure that height is 0. So 0 equals -5t minus 2 squared plus 21. And now I could solve this. So subtract 21 on both sides, divide it by the 5, so 21 over 5 is equal to t minus 2 squared. If you square root, you get plus or minus 21/5 is equal to t minus 2, which means that t is going to be 2 plus or minus the square root of 21 over 5. Now we need to evaluate both of those to see which the one is we actually need. So we'll put our calculator off on the side. Okay, so 2 plus the square root of 21 over 5. Here's one solution, and it says to the nearest tenth. So t could either be 4.0 seconds, that's one of them, or the other one, 2 minus the square root 21 over 5, enter. Or it's negative 0.049 seconds. Now, I can't really have a time that's negative because I can't go backwards in time, so I know my only possible answer is 4.0 seconds. Right? I can't have the other one, it doesn't fit the context. Okay, so completing the square is quite helpful if you can't factor things, and I can solve all these questions algebraically. Sometimes they're not factorable, which is possible. Sometimes we need a different method altogether. The quadratic formula will work every single time, so will completing the square, but sometimes we aren't going to have real roots. Sometimes there are no x-intercepts, and I can't solve it anyways. The quadratic formula gives us a way to check if I'm even going to have roots to begin with, so maybe I don't even have to try to solve it to know that. Okay, and that's what we'll talk about in the next video. So you'll find, again, all these links in the description if you want a copy of anything that I did here. And maybe I'll link Desmos as well. If you don't know where that website is, I can do that for you as well. So we'll see you in the next one where we talk about quadratic formula. And there's one video left after this where we'll talk about some of the applications and word problems, all the things that we can really start to put together with this. So we'll see you in the next one, and until then, take care.